All right, I'm going to get started here. Today we're going to look at the fetch execute cycle. And we did cover this last week. This was part of the architecture and hardware chapter. But now we're going to look at it in discrete detail because I'm going to run a simulation that demonstrates how the fetch execute cycle operates. Let's recall we're really looking at input processing and output, that fundamental model of computation. And recall I stated it applies to the finely discrete granular level of the CPU, but it also applies to the macro granular level of an information system. So again, we're looking at the von Neumann architecture. Where we are, by the way, is if I look at lecture modules, LM2 architecture and hardware, it is located here in the submenu.
Oh, okay.
So here we are, and I'll scroll down. This is the recording from last semester, and I am recording today, so I'll put up the new recording sometime today or later. So let's review. The CPU is comprised of the arithmetic logic unit, represented by the acronym ALU, and control unit. These are the two major components of the CPU. It also has registers and buses internal to it, but it also has a bus to the RAM, and it integrates with the RAM. So I'll ask again, RAM, comprised of bytes. The byte is the smallest addressable unit. There are two things associated with every byte. Does anybody recall what those are? Contents and address. So I get to the contents by using the address. So again, we're looking at the fetch execute cycle, which is shortened because it's actually the fetch decode execute. And there's actually even another step in there that's implicit, because we're going to look at the program counter. It's actually fetch, increment program counter, decode, execute. And again, the textbook adds that store component as well. So just to present what we're going to look at, the registers, there are many registers for control. And note that the simulation, the architecture I'm about to show you is a very simplistic architecture. It's probably representative of the Texas Instruments computer kits that were available in the 70s. Before there were production computers, people were making their own, soldering them together. There we go. Essentially, that's what we're looking at. Yes, a very simple instruction set, simple architecture. So we're going to see several registers used for control: the instruction register, IR, program counter, PC, index, and stack pointer. And we're not going to look at the index and stack pointer at this point. We're also going to see some registers for working with memory: the memory address register and the memory data register. And recall, again, every byte has two things associated with it: its contents and its address. So we use the memory address register to supply an address to pull down the contents into the memory data register. And note that this communication or transfer goes both ways. So I have information coming from RAM to the CPU, but the CPU may also store information back out to RAM through this mechanism. I have two registers used for execution: the accumulator, shortened for ACC, and the results. And I also have flags registers, because again, the arithmetic logic unit is performing arithmetic operations, but I also need to control execution. And you see this if you're taking programming and logic: if, then, else. You're choosing between two execution paths. Well, how does this actually take place? Well, if A is greater than B, then do this, else do something else. How can I represent this essentially Boolean analysis or reference? I can perform addition and subtraction, right? If A is less than B, I can always perform a subtraction and look at the result. Is it positive or negative? So the arithmetic logic unit can be used for control to control execution. So I have flags registers that will indicate the result of arithmetic operations. Is the result 0? Is it negative? Was there a carry? Was there an overflow? So now, returning to our analysis of architecture. Every architecture has an instruction set. These are the machine instructions that it recognizes. And recall, when I was presenting hardware, in the textbook, we present it from a generational perspective, right? Generation 1, vacuum tubes. Generation 2, transistors. And I stated that there were equivalent advances in both operating systems and programming languages. So with Generation 1, vacuum tubes, you had to essentially rewire the computer to do anything. Everything was done down at the machine language instruction level, ones and zeros. So if I wanted to program something, essentially what is the opcode for add? And I'll make this up, 10111, whatever. And I then want to add something to the memory address of location, whatever, 10111. I'm doing everything in machine language. Humans, we do not do well in this. So the second evolution, or second generation of programming languages, was assembly language. Assembly language created a short mnemonic, essentially, for every operation in an opcode. So for subtraction, it would be a 3-letter SUB. Store, STO, or STA in this case, when we look at register transfer logic. With assembly language, it was easier to program. Now I would have to, once I wrote a program in assembly language, I would have to convert it or assemble it into machine language. So there'd be a specific assembler, which is a program, which would essentially transfer or translate my assembly language instructions into machine language instructions. Something to note about assembly language is there's a one-to-one correspondence between every assembly language instruction and every machine language instruction. So for every machine language instruction, there's an assembly language instruction, and vice versa. This is different when we move to third generation languages and fourth into higher level languages. And I'll give you an example. Say in Java, program logic 1. And I have the expression or the statement, z gets x plus y. Well, from a programming perspective on a high level language, that's just one line, right? But that would need to be compiled into machine language to be executed. And what would actually be required? What did I say? I'll change a little. Z gets x plus y. Well, I would have to move x into the accumulator. I would then have to perform an addition of what's in the accumulator. I just moved x with the memory location that is y. Then I would take the result and store that back to memory. So minimally, that one high-level language, z gets x plus y, would be at least 3 or 4 machine language instructions. So that's different than what we're looking at here with assembly language. And the example here will demonstrate that. So what are we going to do? Here's my pseudocode for what we're about to do. We're going to read A from the keyboard. We're going to read B. So I'm going to read in a value for A. I'm going to read in a value for B. I'm going to add A and B, and then I'm going to write and store it in Z, and then I'm going to write Z out to the screen. So here's my pseudocode. Now let's take a look at what it would be in assembly language, and specifically, again, this is register transfer logic. So register transfer logic is essentially a generic assembly language. So what did I do? I read A, I read B, I added A and B and stored it in Z and wrote add Z. In assembly language, I'm going to read something in. I'm going to store what I just read in, 63. I'm going to read in another value. I'm going to add this value I just read in to what I previously stored in location 63, and then I'm going to output it. So these are the assembly language instructions in register transfer logic for the program we're about to run. Note that I've included the machine language instruction here. So the machine language instruction for in is 5,000. The machine language instruction for STA63 or store 63 is 2063. Again, in is 5,000. Add 63 is 3063. These are the machine instruction set. So when engineers design this, they're actually ascribing these codes for every operation that the machine itself, the CPU, can execute. Now let's look at this again in a little more detail. If I look at STA63, which is much more meaningful to me than 2063, if I didn't have assembly language and I wanted to understand what this machine instruction is, I'd have to go to a table. Well, what is the opcode? I'd have to understand that the first two hexadecimal digits here, and I'm going to give you that right there, correspond to the opcode, and the second two correspond to the operand. So I have the opcode and the operand. And in some ways, this is analogous to what you're doing in your Linux labs, right? You have an operation, ls. And then you give it a option, -a, -l. Or in some cases, in Linux, of course, we have both options and arguments. I could change directory into a subdirectory, cd space CISS100 from the Linux lab. So we have our assembly language instruction, what it would actually be translated to by the assembler. So if I were to write this program and assemble it, the resulting machine language executable would be 5,000, 2063, 5,000, 3063, 6,000, 7,000, etc. Okay, so let's jump right into the simulation. So there are several programs. You could write your own program and run it on this, but I'm going to do the add two numbers, which is displayed here. So I have in STA63, in, add 63, out, and halt. So this looks familiar to us. So let me click Run Simulation here. And let's look at this in detail now. So actually, I'm set up to execute the first instruction, but I'll get to that in just a minute. Pardon me. So the CPU. The two main components of the CPU that we're most familiar with are the arithmetic logic unit, ALU, and the control unit, the CU. These lines depict the buses, so I can see the bus structure. So I see that the control unit has a dedicated pathway to the instruction unit. This is the program counter, and I see a counter here because the program counter will continually be incremented. Recall the fetch execute cycle. Fetch instruction. Increment PC, program counter, which the textbook kind of just glosses over. Decode the instruction, execute the instruction, and then of course the textbook adds the store. Here's the memory address register with a dedicated bus to RAM, and the memory data register with a dedicated bus to RAM. So the CPU, to interact with the RAM, sends the address through the memory address register via its dedicated bus to the particular location in RAM, and that contents is brought down into the data register. And again, this goes both ways. So if I want to store something in RAM, I'm also going to use the memory data register. Over here, we see the value of the data bus. This isn't an actual register. All this is here is to show us what is the line state of this bus, the bus that connects the ALU to its various registers. Here is the flags register, 0, negative, carry, and overflow. And if I look at this line state, 0, 0, 0, 0, is it 0? Yes, 1. So the flags register also gives us a Boolean interpretation of the state of the bus. And recall, Boolean is true, false. So we saw with binary, we can represent numbers with it, but the ones and zeros can also represent truth values because this is our control. Again, going back to the Java example, if A is greater than B, then do this, else do this. Well, when I say if A is greater than B, what's the truth value? And how would I determine that? Well, I could just perform subtraction, right? A minus B, if it's positive, it's greater. A minus B, if the result is negative, obviously it's less. So just through arithmetic operations, I can determine mathematical equivalents or relationships. What else haven't I said here? Take a look at this data bus. This again, 0000, is representing hex, hexadecimal. What is my word size? What is my bus width here? Whenever you know it, let me know. Well, if these are hexadecimal digits, every hexadecimal digit corresponds to how many bits? You need to know this. Every hexadecimal digit corresponds to 4 bits, right? That's the way we translate between them. Recall what we did. So if I have 4 hexadecimal digits, how many bits? 16. So my word size is 16, or my data bus is 16. So this is a 16-bit computer. We now have the background to perform this analysis. So this current program here it is in assembly language. Well, it's stored in memory. It's up in RAM. And if I double-click RAM, if I go all the way back to location 0, what do we see? 5,000, 2063, 5,000, 3063. Those were the corresponding machine instructions for this assembly language program. Okay. And again, if I look at my memory addressing, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, everything here is represented in hex. It's actually represented in binary, but for us humans, we don't deal well with binary real well. So everything is represented in hexadecimal. So now I'm going to begin the simulation. We're going to look at that fetch execute cycle, which is actually fetch, increment PC, decode, execute, over and over. Every time I hit the play button, essentially is going to correspond to a clock cycle. And again, this is very simple. I have no pipelining. There's no dual core, quad core here. There's no graphics unit. There's no anything else, floating point unit. We have a base system here. So I'm going to hit play. So what do we know? What has to happen? The program counter was copied to the memory address register, and immediately the program counter was incremented. The program counter is expectational. It's always going to point to the next instruction to be executed. So we're already into the fetch execute phase, so it's actually pointing to the next if we were to run another fetch execute. And this is important. We'll look at this when we get to operating systems, because today's systems, we're not just running a single process in memory. I'm running 10, 20, 100. Depends on what system you're running. So processes are always being suspended and restarted. How do they know where to restart their execution? The program counter, right there. It points to wherever they left off. The program counter knows where to pick it up again.
Which is the program counter?
The PC.
The PC. Okay.
I'll hit play again. Memory address register sends that location up. It's decoded in RAM. It's going to bring down that first 0000 instruction, which we saw was 5,000, corresponds to the in. Okay, I fetched it. We need to get to decode it, but it is going to be transferred. And in future iterations of this, it'll actually just do it. It'll look like a single instruction is going straight from RAM to the memory data register and into the instruction register, when it actually may take 2 clock cycles as it is right now. So the memory data register is getting moved to the instruction register. And I see that the next thing that has to take place is I need to decode this instruction. And every instruction has an operand and, yes, opcode and operand. So I'll hit play, decode 5,000, hit play again. It's now going to execute it. And we know that the execution, it's waiting for me to add something. So I'm going to say 4. Hit enter. And I see 4 shows up in the memory data register. And I still have yet to complete an entire fetch execute cycle. Why? Well, I have this 4 in the memory data register. What would happen to this 4 if I tried to fetch another instruction? It would blow it away. It would overwrite it. So the computer knows it needs to store it somewhere. So it's going to store it at the next clock cycle into the accumulator. So 4 is now in the accumulator. I have now completed 1 fetch, decode, execute cycle. I'll hit play again. I'm going to start it for the second time. So I've completed in. The next one will be store 63. And now we can predict what's going to happen. As soon as I hit play, the program counter will be copied to the memory address register. Memory address register location will go up to location 1 and bring down the instruction that's located at memory address 1 into the data register. The data register will then transfer this to the instruction register. The control unit will decode the next instruction, which of course we know corresponds to STA63 or 2063. It will then get executed, and to execute store 63, I need to store this value back out to RAM. So this value 4 somehow has to get to the memory data register, and the value 63 has to be in the address register so that I can store value 4 in 63. So let's step through it. So PC 1 goes to memory address register 1. Increment PC, 1 plus 1 is 2. Memory address 01 goes up to RAM, pulls down the value 2063. 2063 will get transferred to the instruction register. And now we're paused for the next clock cycle, waiting to decode 2063. So when I do this, the operand component, the address 63, will move to the memory address register. In the next clock cycle, 4 from the accumulator will be put out to 63. And you see why we had to do this in separate clock cycles, right? I can't have 2 things on this bus at the same time. I had to move the address to the memory address register, and in the next clock cycle, because I can't have 2 things on that bus at once, the 4 will get moved to the data register. Now, in the next clock cycle, I can store that value 4 at address 63. So go up, locate address 63, value of 4 comes up, and gets stored. And now take a look. If I double click on RAM, and again, I apologize for the font size. If I scroll down with my horrible eyes, 04 is now at location 63. And there's something else here I'm going to introduce now. We understand the distinction between a program and a process. Program sits on storage. A process is an active dynamic entity that resides in memory. So when I execute a program and it becomes a process, the process has resources allocated to it by the operating system. What resources? Well, it has RAM, right? It's in memory. It's been allocated RAM. It has CPU execution cycles. It may have open files. It may have an open internet connection. So many things. It may access a printer. Going back to the memory, when a program is executed and it becomes an active process, it has 3 segments in memory. It has a code segment, a data segment, and a stack segment. And we see this. I have the data down at location 63. The code, right at the beginning, 0001, right? That's the executable machine instructions with the code. Also have a stack segment. I'm not going to get into this now, but this understanding is critical because when it comes to hacking and security, one of the most often used hacks is buffer overflows. Whereas if I can continually write to your stack segment, pushing into the code segment, and if I can inject executable code into your code segment, I can take control of your computer. So this is the stack overflow or buffer overflow that you'll come to hear about in computer security. And if we don't have this understanding, if you're just out there writing code without this understanding, you're writing code that could be vulnerable. So it's kind of what distinguishes us from, the programming for dummies. So this is absolutely critical knowledge. Okay, so I'll close this. So what did I do? I've just completed my second fetch, execute, decode cycle. First one was reading something in. Second was storing what I just read in into memory location 63. And again, 63 hex. We're going to start our next fetch, execute cycle. So again, thinking in advance, what's going to happen? PC 2, program counter 2, will get moved to the memory address register. I increment the program counter. So it's looking at the next instruction. So should my process be interrupted here, it knows where to start again. It's not going to do the same instruction twice. I'm going to go up and fetch whatever is at location 2 and bring it down into the memory data register. It's going to be transferred to the instruction register, where it will be decoded and then subsequently executed. And the next instruction is in. So I'm going to read something in. We've already seen this, so I'll kind of fly through this as quickly as the simulator will allow me to. So 2 went to the memory address register. PC was incremented. 2 goes up to locate the address in memory and RAM. Bring down the instruction, 5000. We've seen this before. Gets transferred to the instruction register. And at which point, we're going to be waiting to decode. In the next clock cycle, we decode 5000. It's going to wait for me to input something. 6, yeah.
So can you just real quick explain again what exactly the program counter is for? Because it's just going up 1 digit each time.
Exactly.
Is it just counting how many cycles it goes through?
No, it's counting what instruction. You've seen in programming logic, if you're in programming logic, by default, execution goes sequentially.
Yeah.
From one instruction to the next.
Counting what instruction it's on.
It's pointing to. It's actually giving direction on what instruction is to be executed next. Okay. Now, it can be changed because you can have jumps, if then else. So there are times when you're not actually performing the next sequential instruction. So the program counter, yes, it keeps track of where it is, of what's to be executed next. And it's, again, expectational in that regard.
So from what you just said then, with the skipping instruction, it would be, if we're on number 3, for example, and it comes up with the if-then statements that you're talking about. If it's like, if A, do instruction 4, but if it's B, do instruction 6.
Something else. Yes.
4 and 5.
Yes.
Okay.
Right. And that would be a branch, down in assembly language, which would actually change that value appropriately to the correct address. And this is where, boy, I'm going to really get ahead of myself here. I just spoke about stack overflows, buffer overflows. If I could inject a statement there and change that program counter to point somewhere else in memory where I have waiting for it a set of instructions to take control of your system and compromise it, that's all I need to do. All I need to do is change that program counter to point to the next instruction that I want the computer to execute. Yeah.
All right, sorry about this question.
That's good.
So when grandma clicks in her email, and downloads an executable, and it goes somewhere, that's going into the RAM, into the registers,
yep.
And that's what you're saying. If they're pointing to an instruction,
that's different.
That's different.
Okay.
Okay.
That's not a stack overflow or a buffer overflow compromise, right? And we'll get to that too when we get to security and web. Yes. So where was I? We have 5,000. Did I just 4. Okay, 6 was being stored in the accumulator. Recall that when I read it in the last time. I can't leave it in the data register because that will be overwritten by the next fetch cycle. Okay, so I'm in the next. Nope, I read the 6 to the data register. So, okay, I'm in the next fetch. Kind of lost my place there, which means the memory address register got 3. Program counter was incremented to 4. Goes up to location 3, brings it down. I think it's 3063. I've been doing this too much if I have this memorized. Actually, just from last class. 3063 gets transferred to the instruction register. My next clock cycle, I will decode 3063, which is add 63. So I'm adding the contents of memory location 63, which I just retrieved, to what's in the accumulator. So to get what's in 63, what do I need to do? I need to load the memory address register with 63 and then bring down the contents. So 63 will go to the memory address register. And then I will bring the contents of 63 down to the data register. And now I can perform that addition of what's in the data register to what I previously stored in the accumulator from my last read. So 4 plus 6. And we'll go into the results, A. So it should, again, hit us right in the face that we're dealing in hexadecimal. And I can read the status flags. And again, the status flags are resulting from the data bus themselves. And I'll stop here. I won't go. The next one is to output it. You could step through. It's essentially go out. And then, of course, every program should halt. So fortunately, look at that. We're done early. I'm going to let you go at this point. Again, please don't fall behind with the Linux labs. It's critical. If you stay up on it, especially if you practice a lot, you will fly right through the course, okay? You'll have no concerns whatsoever. If you fall behind, as in anything else in computer science or math, which is, you know, analogous to it, it will be bad.
When I submitted my Linux plan and I noticed Sunday, you rated 4 and it's a fail, you read.
Yes, so look at your results. And again, I grade them pass fail. So if you have one little glitch, you know, I'm not looking for 100%. I'm looking.
Will you correct?
Yes, I will. I'm looking for an understanding. I will make a note on what is incorrect and send it back to you. And you can resubmit. As long as you understand it. You know, if you make, by the way, if you make errors, people will make errors. You know, I have fat fingers. You know, LS minus L, and sometimes my thumb won't hit that space bar. Okay. Obviously, that's not understood by the operating system. It's going to give me an error message.
Yeah.
Just move on. I'm going to see that. I understand it's just, you know, fat fingers, whatever, moving too quick, not enough coffee, late night work, whatever. I'm not looking at, you know, okay, you have 5 errors in there. No, I'm not looking at that. I'm looking at, did you finally get it? And so I'm looking for demonstration of understanding.
That's what I did yesterday. I did too many errors.
Yeah. What was that? I'm sorry.
How do you resubmit? Because I had this
Yep. Oh, you can resubmit. You get unlimited submissions.
clear off something.
No, you just go. If you just go back to the assignment and upload it again. And actually, my view, I see your last one. So fortunately, I look at your last one. If it's correct, I don't have to look at the previous ones. So that's what I'm doing. Have a great week.